Last time we ended with the Aufbau principle, which says that as an atom fills itself with electrons, it builds them up. That's what Aufbau means, build up. Builds them up from the lowest energy sublevels to the highest energy sublevels. Only when the lower energy levels are full do the electrons begin to go into the higher energy levels. We'll take a look at this with respect to carbon. Carbon has 6 electrons because it's element number 6. The first 2 electrons can go in the lowest energy sublevel, which is the 1s sublevel. But s sublevels can only contain a maximum of 2 electrons, and so when that's full, the next 2 electrons in carbon have to go in the 2s sublevel. That can only contain 2. All s's can contain only 2. So the next 2 have to go in the p sublevel of shell 2. P's can contain up to 6, and we could keep building this atom if it had more electrons by putting more electrons in the p. Now, drawing these X's on charts like this isn't very practical. So today we're going to look at 2 ways of describing where the electrons are in an atom that's sort of quick and shorthand and gives us a good picture of what the atom is like. And that will help us make chemical change predictions in the future. And in the video following this one, we're going to learn about 2 more ways that are even simpler and, in fact, even more useful. The first method of describing the atom that we're going to look at is called electron configuration notation. In electron configuration notation, we list what subshells are occupied by electrons. And then we list how many electrons are in each occupied subshell. This is the format that we'll use. We will first write down the principal quantum number. We'll follow that by the letter S, P, D, or F for the sublevel that we're talking about. I'll just use X for sort of a generic sublevel. And then we'll superscript after it the population in that subshell. And I'll use Y to represent the electron population. Let's get started with some examples. Let's look at hydrogen first. Going back to this chart, we recall that hydrogen had 1 electron in the 1s sublevel. So in electron configuration notation, we would say that the 1s sublevel has a population of 1. Let's look at helium. Helium had 2 electrons, and both of those electrons went in the 1s sublevel. So again, we would write 1s as a sublevel that's occupied, but now the population is 2. Now note that this should not be read 1s squared. I know in math when we superscript a number after a variable, that's squaring it, but that's not what that means here. That 2 is the population of the sublevel. Let's try carbon. Remember when we did the Aufbau work on carbon, we found that 2 electrons went in the 1s, 2 electrons went in the 2s, and 2 electrons went in the 2p sublevel. So we have 3 sublevels that are occupied, 1s, 2s, and 2p. And it turns out that each one has a population of 2. So we would write 1s, 2, 2s sublevel, population 2, 2p sublevel, population 2. When you're writing these electron configuration notations, you can always kind of check your work by adding up all the populations. Those should add up to the atomic number for the element. In this case, they do. Well, it's your turn. Give the electron configuration notation for lithium, then try beryllium, then try boron. In your follow-along notes, you've got a copy of the chart that we were using, and that might help you. All right, if I'm looking at lithium, lithium is atomic number 3, so that means I have to place 3 electrons on this chart. The first 2 electrons can go in the 1s sublevel. The next electron has to go in the 2s sublevel. So lithium, I can see, has got a 1s sublevel occupied with a population of 2. The 2s sublevel is occupied with a population of only 1. And so there's the electron configuration notation for lithium. Beryllium. Beryllium is element number 4, so I'm going to have to populate 4 electrons into this chart. The first 2 go in the 1s sublevel. The next 2 can go in the 2s sublevel because s's can contain up to 2 electrons. I have 2 sublevels occupied. They are 1s and 2s, and both of them now have a population of 2. There's the electron configuration notation for beryllium. Boron. Boron's element 5. So that means I'll have 5 electrons that I have to put in here. The first 2 go in 1s, the second 2 go in 2s, and the fifth one has to go in the 2p sublevel. So I have 3 sublevels that are occupied. 1s is completely occupied, that's 1s2. So is 2s. And 2p has 1 electron in it. So there's the electron configuration for boron. Carbon we've already done. Okay, now that you've seen some of these worked out, this should be pretty easy for you. Try the electron configuration notation for nitrogen, oxygen, fluorine, and neon, and I'll give you the answers. Next is nitrogen. Nitrogen is element number 7, so 7 electrons. The first 2 electrons go in 1s sublevel. The next 2 go in 2s. Now P's, remember, can contain up to 6 electrons. So I have 4 down, I need 3 more on the chart, so I can put all 3 of them in the P sublevel. So there are 3 sublevels occupied. 1s has 2, 2s fully occupied with 2, and 2p is partially occupied with those 3 electrons. 3 and 2 is 5, and 2 is 7, so my check turns out to verify what I've done. There's the electron configuration notation for nitrogen. Oxygen's next. It's number 8. So 2 electrons in the 1s, 2 electrons in the 2s, and that gives us 4. I need 4 more in the 2p. I can fit 4 in there because I can go up to 6 there. So again, I have 3 sublevels occupied. 1s, 2s, and 2p. Population of 1s is 2, 2s is 2, and 2p is 4. Fluorine. Fluorine is element number 9, so 9 electrons go in my chart. 2 in 1s, next 2 in 2s, and then I have 5 more to go. 1, 2, 3, 4, 5. 3 occupied sublevels, 1s with 2, 2s with 2, and 2p with 5. There's the electron configuration for fluorine. Now you probably are noticing a pattern here. 1s is always going to be 2 from now on, 2s is always going to be 2, and 2p just keeps increasing by only 1. So for neon, the very next element, number 10, I can expect to find 2 here and 2 here. I'll always have 2 in 1s and 2s from now on. But that gives me 4, and I need 6 more electrons. They can all fit in the 2p sublevel because p sublevels can contain 6 electrons. So I still have only 3 occupied sublevels, 1s, 2s, and 2p, but now they're all full. 2 in each of the s's and a 6 in the p. There's your electron configuration for neon. Another kind of notation that's useful and actually gives us a little more information is called orbital notation. Orbital notation is almost a sort of a stylized picture of the electron structure of the atom. In orbital notation, a set of parentheses represents an orbital in an atom. And inside those parentheses will go arrows that represent electrons. Now, electrons have a property called spin, and the spin can only have 2 different values. One is called spin up, or plus 1/2, and the other one is spin down, or minus 1/2. It's actually almost a quantum number. It has only 2 values. And those arrows are going to go inside of the orbital, inside the parentheses, to represent the electron. Now, the parentheses are my way of doing it, and there are other ways that different teachers and different textbooks use, sometimes just lines or sometimes boxes, but parentheses are quick and easy to draw, so that's what I use. One rule that we have to abide by is when 2 electrons are in the same orbital, their spins have to be opposite. So you can't have 2 up arrows, you can't have 2 down arrows, you have to have 1 up and 1 down if there are 2 electrons in the same orbital. And typically it's just kind of a convention. If you have only 1 electron in an orbital, you usually write it spin up, but you wouldn't have to. So let's look at hydrogen as an example. The electron configuration notation for hydrogen was 1s1. So that means there's a 1s sublevel. 1s sublevels have only 1 orbital in them, so I draw 1 set of parentheses. The population of that sublevel is 1, so that means I'm going to draw 1 arrow in my orbital. Helium was the next one. The electron configuration notation was 1s2. 1s sublevel has only 1 orbital. It's an s orbital. And this 1s orbital has a population of 2 electrons now. So I put 1 in here, spin up, and the other one I put in here, spin down, because they have to have opposite spins. So there's the orbital notation for helium. Lithium. Lithium has got an electron configuration notation of 1s2, 2s1. So now I have two sublevels, and I'll have to illustrate both of them. Both of them are s sublevels, so I only need two parentheses. Here's my 1s sublevel, and here's my 2s sublevel. The 1s sublevel is full. Got two electrons in there. 2s is not, so there's only a single electron in. Beryllium was 1s2, 2s2. So again, I have only those two sublevels, 1s and 2s. But now they're both full, so I have spin up and spin down electrons in both of the orbitals. Well, next time I'm going to have a p sublevel start showing up here. And when a p sublevel shows up, I have an example of a case where there's more than one orbital in the same subshell. When that happens, I want to show all the orbitals, even the ones that are empty, even if there's no electron in there. And the other thing I want to do is I want to draw a line over them or under them. I typically do it over them to show that they're all in the same subshell, so it keeps things clear. For example, if I was going to do boron, boron is 1s2, 2s2, 2p1. I would write my 1s sublevel, just one orbital, my 2s sublevel, which is again just one orbital, and then I'm going to write 2p as three orbitals because p sublevels have three orbitals. And even though this sublevel is not going to be fully occupied, I'm going to draw all three of them. And I'll put a line over the top and label that as 2p. 1s is full for boron, so I put a spin up and a spin down electron in there. 2s, spin up and spin down. And 2p, well, there's only one electron in one of the orbitals. I'm going to pick the first one, but I wouldn't have to. I'm going to give carbon a try here. Carbon, if you recall, was 1s2, 2s2, 2p2 for electron configuration notation. So to draw my orbital notation, I'm going to draw my first orbital, the 1s, and it's full, so I put two electrons in there. 2s is also full, so I'll draw one orbital and put two electrons in there. And then 2p has three sublevels in it, so I draw all three even though they're not going to be full. And I put a line over the top to indicate that they're at the same subshell, and I'll label it 2p. Well, now I have a problem because I have two electrons in there. And what do? I could put both of them in the same orbital. I could put one in each of two orbitals. What am I supposed to do? Well, it turns out that there's a rule for that, and this isn't an arbitrary rule. This rule actually follows what the electrons do in nature. It's Hund's rule. Hund's rule says when you have more than one orbital in a sublevel, these electrons are going to occupy the greatest number of orbitals possible. In other words, they're going to spread out as much as they can. No two electrons are going to go in the same orbital if they don't have to. So going back to carbon, that 1s sublevel and 2s sublevel, well, they have two electrons in them. But now when we get to our 2p, we know what to do. I want to spread those two electrons out as much as I can by giving them each their own orbital. I put them in the first two orbitals. I wouldn't have had to. I could have put one in 1 and one in 3. And I put them both spin up. Again, I wouldn't have to. That part is arbitrary. But you do have to put them in separate orbitals. Okay, you practice this. Give orbital notation for nitrogen, oxygen, fluorine, and neon. Nitrogen was 1s2, 2s2, 2p3. So I'm going to put my 1s sublevel, my 2s sublevel down, and I'm going to illustrate my p sublevel with three orbitals and a line over the top. For nitrogen, 1s is full, 2s is also full, and 2p has three electrons, but I'm going to put each electron in its own orbital because of Hund's rule. Oxygen, 1s2, 2s2, 2p4. So 1s and 2s are full, just like before. Here's my 2p sublevel. I've got four electrons. The first three I'm going to put in their own separate orbital. But I can't fit the fourth one in its own orbital because there's only three. And so I have to double this one up. I'll put it in the first orbital. Fluorine is 1s2, 2s2, 2p5. 1s is full, 2s is full, and my 2p sublevel is getting full. I've got 5 electrons. The first 3 I'll put in separate orbitals, and then the last 2 have to double up. Neon, 1s2, 2s2, 2p6. So the 1s sublevel is full, just like everything in this row. The 2s sublevel is full. And now the 2p is finally full because I have 6 electrons. All 6 of them are doubled up with a partner. Okay, it's time to stretch out a little bit and go to sodium, magnesium, aluminum, and silicon. You're going to have to probably look at the chart again, the energy chart, to figure out what the electron configuration notation should be, and then build an orbital notation from there. Sodium is element number 11, so I've got to put 11 electrons in here. I think I'm going to give myself a little head start on orbital notation by actually drawing some orbitals in here. 1s is 1 orbital, 2s is going to be 2 orbitals, 2p is going to be 3 orbitals, a 3s will be 1 orbital, and a 3p will be 3 orbitals. Now, as I'm putting my 11 electrons in here, the first 2 are going to go there, the second 2 are going to go there, the next 6 can go here, spin up and spin down, and then that gives me 10. 6 and 2 and 2 is 10. So my next electron is going to go in a 3s orbital by itself. So sodium is 1s and 2s full, 2p full, and 3s half full. The next one I have to do is magnesium. Magnesium's number 12. Well, you can probably see what's going to happen here. I'm going to just fill that next orbital. So magnesium looks just like sodium. In fact, I'll just cross out sodium and I'll add another electron. That's what it looks like. Next element, what's the next one in line? It's aluminum. Aluminum is element number 13. So my 12 electrons fill up that 3s sublevel. So now it's time for me to build a 3p sublevel. It has 3 orbitals in it, so I draw all 3 of them. Aluminum has 13 electrons, 1 more than magnesium, so I'm just going to put 1 more electron in one of those orbitals. So I'm going to cross out magnesium. This is now my aluminum orbital notation. Next is silicon. Silicon is number 14. 1 more electron. By Hund's rule, it has to go in a separate orbital. So, cross out aluminum. Now I'm silicon on my orbital notation, and it's got an electron in that second orbital. Or it could have gone in the third. Next one, let's just keep going. Phosphorus. Phosphorus is number 15. 1 more electron. It can go in its own separate orbital in the 3p. So there's the orbital notation for phosphorus. Next, sulfur. Sulfur is number 16. That means 1 more electron. It can't fit in its own orbital. I've got to double it up with one of the 3p electrons that's already there. So in my orbital notation, that's all that changes. Next, chlorine. Chlorine is number 17. So, 1 more electron right in there. And then finally I get to a noble gas, argon. And argon has 18 electrons. That means it's going to fill that 3p sublevel. Now you may recall that when we did neon, we filled that up. Now we're at argon, and we've just filled that up. When we were at helium, we had just filled the first shell. These shells always end with a noble gas. and the row on the periodic table always ends with a noble gas. So that gives us some important hints as to how we can do this quickly and easily by just looking at the periodic table. And that's good, because when we add more shells to this energy level diagram, things get complicated fast. There's the 4s, there's the 5s, and there's the 6s. It would be very difficult to memorize this entire chart and use this as a way of figuring out what sublevel comes next. It's hard to even keep track of it. Even with the color coding, it looks like a mess. So, we have a valuable shortcut that's right on the periodic table. Here's this pattern. The first row of the periodic table fills the 1s shell. That's hydrogen, and that's helium. The next two rows, 2 and 3, fill the S and the P subshells for their row number. So this is going to be 2s1. It's going to end in 2s1. Well, that's lithium, 1s2, 2s1. And this one, 2s2. Well, that's beryllium. Here's 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, as we go from boron to carbon to nitrogen to oxygen to fluorine to neon. And in the third row, that repeats. 3s1, 3s2, and then over to 3p1, 3p2, and so on, all the way up to 3p6. So whatever column we end in, that dictates what's going to be the ending of the electron configuration notation, and it's going to be n equal to the row number. Things get a little more complicated in the next two rows, but it's still a pretty easy pattern. The next two fill S for their row, and as you're going across the row here, it's 4s1, 4s2, but then when we get to this next section, we notice that instead of 2, like there are 2 electrons in an S subshell, we have a group of 10 columns. Well, what has 10 electrons in it? A D subshell. So we're filling D subshells as we go across that middle part where the transition elements are. However, they're not D's for the row number, they're D's for the previous row number. So if we're in row number 4, it's going to be 4s1, 4s2, but it's going to be 3D, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Then once the D's are filled, we go back to the row number for the P's. So if we're in row 4, these are 3 D's, but these are 4 P's, 4p1, 4p2, and so forth, all the way up to 4p6. And the fifth row is the same pattern. The next two get even more complicated, but fortunately we don't have to work with them too often. First of all, we fill S for the row number, so 6s1, 6s2 in row 6. Then, all these elements down here, these lanthanides and actinides, they actually belong in there. They're not written in there in most periodic tables. And guess how many columns are there? You might have guessed 14, because there are 14 electrons allowed in the F sublevel. But instead of the F having 1 less than the row number like the D's, it has 2 less than the row number for its principal quantum number. So if I'm in row 6, it's 6s1, 6s2, and then it's going to go down to 4f. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to 14. Then I'm back to my D's, and my D's are 1 less than the row number. So in row 6, that would be 5 D's. In row 7, that would be 6 D's. And then when I get to my P's, I'm back up to the row number again. So row 6 is 6 P's, and row 7 is 7 P's. So with this pattern in place, once you get used to it, you can just read through the periodic table like you're reading a paragraph. Start at hydrogen, write down all the full subshells that you go through on your way to your target element, and then when you get to the last subshell, just don't completely fill it up. Count how many electrons you have to get into that column, and stop there. Best learned by example. Here's an example, phosphorus. Here's phosphorus. phosphorus right there. That's my target. That's where I'm going. I'm going to start at hydrogen. As I go through the first row on my way to my target, I fill the 1s sublevel. These two elements in this block are going to fill the 2s sublevel. So I'm going to write 2s2 because it's full. These 6 are going to fill the 2p. So I'm going to put down 2p6. I'm still not at my target, so I start the third row. The first two columns of the third row fill the 3s sublevel. So I'm going to add to my notation 3s2. Now, I start going into the 3p's here. So I'm going to write down 3p, but I don't go all the way to 6. I stop at 3p3 because it's the 1, 2, third column in. So I go to there and stop, and I write down 3p3. There's my electron configuration notation for phosphorus. No chart needed. Don't have to memorize any complicated looking diagram. I just read it off the periodic table that I already have. Another example, bromine. Bromine's down here. Starting from hydrogen, go first row, that's 1s2. Second row, 2s2 gets me there. Keep going. Next 6 give me 2p. So I'm going to write 2p6. Third row, first 2 give me 3s2. Next 6 are going to fill all the way up through the 3p's. So I'm going to write 3p6. Fourth row, the first two columns are going to give me 4s. Same as the row number. So I'll write down 4s, and I filled it. I went all the way through 4s2. The next 10 columns are going to give me d's, but remember it's one less than the row number. So instead of 4d10, it's going to be 3d10. Next, I'm going into the 4p's. I'm back up to the row number now, but I'm not going all the way in because I only go 1, 2, 3, 4, 5 steps in to get to bromine. So 4p5 is where I ended, and there's my electron configuration notation. Now here's an example that's way down in the periodic table. So this is going to be a kind of a long configuration, and to try and do this on that chart would be nearly impossible. But we can do it on the periodic table pretty easily. PV, right there. There's my target. I'm going to start at hydrogen, and I'm going to keep going through my subshells until I get there. So the first row always fills the 1s subshell. So I start out 1s2. Second row, I have a s and a p. So going all the way through that row gives me 2s full and 2p full. Third row also has an s and a p. So 3s, 2, 3p, 6. I fill those sublevels because I went all the way through. Row 4 starts out with 4s. So 4s2 because I'm going all the way through that block there. Then it goes to 3d, and I fill that. So 3d10. Next I'm back up to 4 for the p's. So that filled 4p. So I add to my configuration 4p6. Row 5 starts with s's. 5s. 2. Goes to 4d. 4d10. Completes the row with the 5 p's. I go back to the row number when I get to the p's. So 5p6 because I went all the way through the row. Next I start with row 6. The first two fill the 6s. So 6s2. Then I have to hop down here and go through 4f. So I went all the way through it, so it's completely populated, 4f14. Then I come back up to here and I go through the 5d's. So I add 5d10 because I went all the way through it. And now I'm finally back up to row 6 again for the p's, and I'm only going 2 steps in. So I finish this off with 6p2. There's the electron configuration notation for lead. It's pretty long. but at least we could do it. The periodic table helps make this possible. Well, I'm going to have you do some practice, as you might imagine, in class, but then I'm going to show you the easy shortcuts. So the next video is going to take what we've learned here, and now that it's become solidified in our mind after some practice, we're going to collapse it down to the part that really matters the most in chemistry.